Bismillahirrahmanirrahim. Assalamu alaikum. My name is Alishba Zainab from BS Chemistry. Today my presentation topic is chemical analysis and weathering test on space grade polymers alias simulated LEO environment. First of all, objectives, so let's start this. To evaluate degradation of space-grade polymers and alloys under simulated low Earth orbit LEO conditions, to study oxidation, UV, VUV, photolysis and atomic oxygen AO erosion, to analyze released volatile and condensable species, to determine degradation kinetics and propose mitigation coatings with implications for orbital debris generation. Materials: polymeric substrates Captain PI, PEEK, FAB, PTFE, epoxy composites. Metallic substrates AI6061, T6TI6Al4V SS316L. AO generation gases: high purity O2 AR have for plasma stability, O3 O2 mixture. Calibration standards: polystyrene film FTIR, gold reference, XPS, NLKs and oxygenates, GCMS, indium zinc, DSC, TGA. Contamination control: siloxanes, D4, D5, phthalates, DEHP. Apparatus: thermal vacuum chamber 10-6 to 10-7 meter bar, ORF oxygen plasma AO source with quartz crystal micropellets, solar simulator UVAB VUV lamps, FTIR ATR mode, XPS spectrometer AIK alpha source, GCMS with cryo trap and TD inlet, DSC TGA with evolved gas analysis, AFM SEM for surface morphology. Procedure: sample preparation. Cut polymer coupons 25 into 25 mm, clean with IPA and bake at 80 degrees Celsius. Polish alloy coupons to radium 0.05 micrometer degrees and passivate stainless steel. Store all samples in N2 desiccator. Baseline characterization. Record FTIR spectra 600 to 4000 cm per centimeter. Perform XPS survey and high resolution scans. DSC TGA runs in N2 and air. GCMS blank runs for contamination check. Exposure matrix. AO flux 10 15 to 1017 atoms per centimeter square per second. Fluence up to 10 to 22 atoms per centimeter square. UV irradiance 0.5 to 1.5 W per centimeter square. Thermal cycling -80 plus 140 degrees Celsius 50 to 300 cycles. Controls: AO only, UV only, thermal cycling only, synergy, arms AO plus UV, AO plus thermal cycling. Volatile capture. Cryo-trap volatiles during exposure. TD-GC-MS analysis post-exposure. Post-exposure analysis. FTIR for functional group changes. XPS for surface oxidation states. DSC TGA for TG-TM shifts and mass loss onset. AFM SEM for erosion morphology. Observations. Captain PI. Surface recession FTIR shows carbonyl lactone growth. XPS OC ratio increase. TG downshift. Peak. Moderate carbonyl formation. Slight crystallinity increase. TG reduction 2 to 6 degrees Celsius. FEP, PTFE, negligible AO, erosion trace CF4 into C2F6 under VUV. Epoxy composites. Matrix oxidation interfacial damage under AO plus thermal cycling. SAM shows fiber pull out. AI alloys aluminium oxide thickening stable morphology. TIC6 aluminium 4, titanium oxide, stable minor sub, stoichiometric titanium oxide acts under high AO flux. SS316L chromium oxide enrichment, volatile GCMS formaldehyde, acetaldehyde, acetic acid, carbon monoxide, carbon dioxide, aromatic fragment trace, fluorocarbons under VUV. Calculations. Erosion yield, where del H is equal thickness lost nanometer is equal effluence atom per centimeter square. Kinetic splitting, carbonyl growth follows pseudo first order kinetic with Langmuir saturation Tg downshift proportional to station density. GCMS quantitation emission rates normalized to fluence Ng per centimeter square per H. Results: Captain high erosion yield OC increase 0.05 to 0.15 Tg downshift 10 degrees Celsius. Peak lower erosion yield moderate oxidation crystallinity reorganization FAB PTFE or resistant degradation only under VUV epoxy composite synergistic AO plus thermal cycling accelerates micro cracking and debris risk. Metal stable mass oxide stoichiometry shifts only. Suggested mitigation coating. Fluoropolymer skins FAB PTF on PI epoxy ALD aluminum oxide silicon oxide nanolaminates for AO resistance UV absorbers titanium oxide nanoparticles for photostability fiber sizing silane coupling agents for composite interface protection. Implication for debris generation, volatile emissions, oxygenates and aromatics contaminate optic and instruments, particular risk, AO plus thermal cycling promotes breaking in composites, lifetime prediction models must integrate AO flux, UV irradiance and thermal cycling synergy to forecast debris generation and surface property drift. Shukriya.